something doesn't add up with 3I/Atlas. In late July, flagship space telescopes like Hubble and JWST captured extraordinary data on this rare interstellar comet. Then, just as its coma balloon passed 300,000 kilometers and report emerged of a green tinge and strange brightening patterns, the official updates went silent. NASA blamed solar geometry and safety protocols. But the abrupt lull stands out when you consider that Oumuamua and Borisov sparked flurries of rapid-fire releases. This information vacuum isn't just fueling wild theories. The lack of timely answers could undermine public trust in how astronomical discoveries are revealed. So what's the real reason for the blackout? And what are we being told about 3I/Atlas? On July 21st, 2025, the Hubble Space Telescope locked onto 3I/Atlas and captured the sharpest images yet of this interstellar visitor. 2.5 weeks later, on August 7th, those images went public, showing a nucleus no larger than 5.6 kilometers across and a sprawling dust plume stretching sunward. By August 6th, the James Webb Space Telescope had taken its turn, using the NIR-SPEC instrument to gather spectra. But for Webb, only technical notes and preliminary comments reached the public. No headline images, just hints that analysis was underway. Gemini South joined in on August 27th, capturing images that confirmed the comet's activity and tail evolution. Those data appear in the public archive by September 4th and 5th, giving researchers and amateur astronomers another look at the growing coma and shifting dust features. Each release landed with a burst of online discussion, but the intervals between them started to widen. After September 22nd, the cadence changed. No new flagship images. No fresh datasets from Hubble, JWST, or Gemini. The flow of official updates slowed to a crawl. For anyone tracking the comet's progress, the absence was impossible to miss. The public timeline, once marked by steady releases, now showed a growing gap. The question wasn't just about what had been seen, but why nothing more was coming out. Observing 3I/Atlas with Hubble or JWST isn't just a matter of pointing and shooting. Both telescopes are governed by strict solar avoidance rules, technical boundaries set to protect their sensitive optics and detectors from stray sunlight. For Hubble, the rule is clear: no observations within 50 degrees of the sun. JWST, with its massive sun shield and delicate infrared sensors, is even stricter, enforcing an 85-degree minimum separation. These angles aren't negotiable. They're baked into the system. If a target drifts too close to the sun's position in the sky, the software locks out any attempt to schedule or execute an observation. The risk isn't just theoretical. Direct sunlight could overheat the instruments, permanently damage detectors, or even threaten the entire mission. As 3I/Atlas moved along its path, its solar elongation, the angle between the comet, Earth, and the sun, shrank day by day. By late August, it slipped past Hubble's 50-degree limit. And just after JWST's August 6th NIR-SPEC run, the comet crossed JWST's 85-degree threshold. At that point, both telescopes entered an enforced blackout. The science teams at the Space Telescope Science Institute, who manage scheduling and operations, had no choice but to stand down. The keep-out zones are hardwired into the mission planning tools. Attempts to override them would trigger automatic safing protocols and could halt all science operations until a full review. This isn't about bureaucratic caution. These are hard physical limits. Even urgent target of opportunity requests can't bypass the keep-out zones. The only option is to wait for the geometry to change. For 3I/Atlas, that means no new flagship images or spectra until the comet's elongation increases again, which orbital calculations predict will happen in early December. Until then, the blackout holds, and the flagship observatories remain silent, not by choice but by design. Hints about 3I/Atlas's true nature began to surface as soon as the first science data trickled out. Hubble's July images revealed not just a dust tail, but a sprawling coma, an envelope of gas and dust stretching nearly 348,000 kilometers across. That's more than a quarter of the sun's diameter, and far larger than most comets at this distance. The most intriguing detail came from early spectroscopic notes. Astronomers started whispering about an unusually strong carbon dioxide signal in the coma. Now, It's important to say that as of late September, no one has published a peer-reviewed quantitative spectrum confirming carbon dioxide dominance. But the hints are there, and the science teams haven't denied it. For a comet entering the inner solar system for the first time, that would be a major chemical clue. Most local comets are water-dominated at this range. Alongside the official releases, amateur astronomers kept pace with their own observations. Several reported seeing a distinct greenish tint in the coma, likely from dicarbon or cyanogen, classic signatures in cometary chemistry, but with a twist. Some observers noted the green was brighter and more persistent than in typical comets. Though without full spectral data, it's hard to pin down the cause. The sunward plume, first caught by Hubble and then Gemini, also became a talking point. Its shape and brightness seemed to shift from night to night, sparking debate about whether surface outbursts or viewing geometry were to blame. Photometry, measuring the comet's brightness, added another layer of confusion. Amateur and professional measurements scattered widely, sometimes differing by more than a full magnitude. Some of that is down to equipment and calibration, but part of it may reflect real, rapid changes in the coma or nucleus. With flagship observatories offline, the scatter in these ground-based reports became the main window into 3I/Atlas's activity. For now, the best available facts point to a comet with an outsized coma, a possible carbon dioxide-rich composition, a sunward plume, and a color profile that refuses to settle. In the absence of new flagship data, each oddity becomes a seed for speculation and a reminder of just how much we're relying on the trickle of amateur and ground-based science. By late September, the silence around 3I/Atlas wasn't just technical. It started to feel personal for the people watching from the ground. Social media threads filled with frustration and speculation. One amateur astronomer wrote, "It's like chasing a ghost. Every night we're guessing what's actually happening out there." Another asked, "Why can't we just see the raw data? What are they waiting for?" The truth is, the pipeline from telescope to public release is anything but instant. Every observation from Hubble or JWST enters a kind of limbo. Once the data are downlinked, they go through calibration, removal of cosmic rays, correction for detector quirks, and background subtraction. For JWST, the process is even more involved. Each NIR-spec spectrum passes through multiple software stages, with instrument teams checking for artifacts or calibration errors. A single misstep can mean claiming a chemical signature that isn't real. Beyond the technical hurdles, there's policy. Both Hubble and JWST operate under proprietary periods, 6 months for most Hubble programs, up to a year for JWST. The principal investigators, or PIs, get first crack at the data, a tradition meant to reward those who designed and won the observing proposals. While some PIs choose to release data early, many wait until their teams have analyzed and cross-checked every pixel. That's especially true for targets as high-profile as 3I/Atlas, where a premature claim could ripple through the scientific community and the press. Institutional routines add more layers. Every press release or headline image passes through multiple agencies, NASA, ESA, and sometimes CSA for JWST. Each group reviews the findings, checks for legal and contractual issues, and coordinates on timing. Even a non-controversial dataset can sit for weeks in this review loop, waiting for sign-off from project scientists and communications leads. For 3I/Atlas, the process slowed further as teams weighed the risks of releasing incomplete or ambiguous results. As one JWST co-investigator put it, "It's better to be right late than wrong fast." With interstellar targets, there's no second chance. All this means that while the public and citizen scientists are hungry for updates, the official channels move at their own pace. The sense of waiting, of staring at the same old images while rumors swirl, is built into the system. For many in the community, the vacuum feels like a wall. For the mission schedulers and data analysts, it's a wall built for caution, not secrecy. But the longer the silence stretches, the more it shapes the conversation, turning procedural delays into fuel for speculation and routine caution into a source of unease. Rumors about 3I/Atlas started multiplying as soon as the flagship telescopes went silent. Some threads pinned the blackout on classified sensors, suggesting that military or intelligence satellites had snapped images the public would never see. Others leaned into panic prevention, the idea that agencies were managing the story, holding back data to avoid alarming headlines about an interstellar anomaly. There's even a camp that claims the data are simply too strange to release quickly, that scientists are scrambling behind the scenes to make sense of something that doesn't fit the usual playbook. The media landscape only adds fuel. Stories about comets like Lemon or Swan, bright, easy to spot, and photogenic, climb social media charts and headline lists. Their visibility makes them algorithm gold. What you can see tonight always wins clicks. In contrast, 3i/Atlas, with its patchy updates and technical hurdles, fades from the trending list. When there's nothing new to show, the vacuum fills with speculation. After the Gemini South images dropped in early September, social media engagement for 3i/Atlas spiked to levels 10 times higher than typical comets, then drifted toward conspiracy hashtags as the data gap stretched on. But the reality behind the scenes is less dramatic and far more methodical. Every observation from Hubble or JWST enters a multi-stage pipeline before anyone outside the instrument team gets a look. First, the raw data are downlinked and tagged with spacecraft telemetry. Then calibration routines kick in. Cosmic rays are scrubbed, detector course corrected, background subtracted. For JWST, this means passing through at least 3 main stages: detector level corrections, instrument calibration, and advanced processing like co-addition and artifact rejection. Each stage is checked for errors, flagged for anomalies, and sometimes rerun if anything looks off. Once the data reach a science-ready state, the principal investigators review them, often under a proprietary period, 6 months for Hubble, up to a year for JWST. Only after the PI and team are confident in the results do they move to the next gate, agency review. NASA, ESA, and sometimes CSA all weigh in, checking for legal, contractual, and scientific issues. Press officers coordinate the timing of releases, sometimes waiting weeks for everyone to sign off. If the data are ambiguous or hint at something unexpected, the process slows even further. A premature claim, especially for a high-profile target like 3i/Atlas, risks a public correction or even retraction. The contrast with earlier interstellar visitors is sharp. When Oumuamua was discovered in 2017, the data poured out almost in real time. Preprints, open debate, and wild speculation all hit the internet within days. Borisov, 2 years later, followed a steady textbook cadence. Images and spectra release on schedule with little drama. For 3i/Atlas, the combination of technical hurdles, cautious review, and multi-agency sign-off has created a slow, uneven flow. The result is a perfect storm for rumor and frustration. But beneath the noise, the pipeline is grinding forward, stage by stage. Each step designed to catch mistakes before they reach the public. For the engineers and analysts inside the process, it's not about secrecy or story control. It's about getting the science right, even if that means waiting longer than anyone would like. The Mars flyby on October 3rd is the next big opportunity for new data on 3i/Atlas. At its closest, the comet will pass just 0.19 astronomical units from Mars, about 28 million kilometers. That's close in cosmic terms, but still far beyond reach of any high-resolution imaging. The ExoMars Trace Gas Orbiter, TGO, carries a Cassis camera, which is often cited for its sharp 5-meter per pixel images of the Martian surface. But at this distance, Cassis faces hard physical limits. In the best-case scenario, each pixel covers more than 300 kilometers. The nucleus of 3i/Atlas, somewhere between 320 meters and 5.6 kilometers across, will be a single unresolved dot. No detail, no shape, just a faint point of light against the background stars. HiRISE on Mars Reconnaissance Orbiter, with its larger aperture, can do a bit better, down to about 34 kilometers per pixel, but that's still orders of magnitude too coarse to pick out the nucleus or any structure in the coma or tail. These cameras were built for mapping Mars at close range, not for deep space targets moving across the sky. Tracking a comet at interplanetary speeds isn't in their playbook. Exposure times have to be short to avoid smearing, and the signal-to-noise drops fast as the comet fades into the distance. So what can Mars orbiters actually deliver? Photometry, a measurement of the comet's brightness at a moment when Earth-based telescopes and the flagship observatories are sidelined by solar geometry. A point source detection from Mars orbit is valuable for tracking the comet's position and activity, especially if there's any sudden outburst or brightness change during the flyby. The data pipeline is fast. TGO and Mars Express can downlink and process these observations within a day or two, barring any technical hiccups. But for anyone expecting a dramatic close-up, it's important to set expectations now. The Mars flyby is about timing, not detail. The real value lies in coverage during a window when every other eye is forced to look away. Perihelion for 3I/Atlas arrives on October 29th or 30th, with the comet passing about 1.36 astronomical units from the Sun. At that distance, it's not a classic sun grazer, but the rapid heating and high velocity still put the nucleus under real stress. So what should you watch for as the comet swings through solar passage and reemerges in December? First, keep an eye on the light curve. Sudden jumps in brightness, especially sharp, short-lived spikes, can signal surface fragmentation or outbursts. But a smooth rise and fall following the expected curve as the comet nears, and then recedes from the Sun points to steady volatile release rather than breakup. Remember, a single brightness jump isn't proof of fragmentation. You want to see a pattern, ideally confirmed by multiple observers. Next, look for changes in the antitail, the sunward-pointing spike seen in wide-field images. As Earth's position shifts relative to the comet's orbital plane, the antitail can flip or fade. For 3I/Atlas, antitail prominence should peak close to perihelion, then rapidly diminish as the geometry changes into December. Tracking its orientation across images is a powerful tool for confirming orbital details and dust behavior. Color matters, too. If the green issue reported by amateurs disappears or shifts after perihelion, that could mean the loss of certain molecules as surface ices are depleted or fresh material is exposed. But only spectra can confirm what's really changing. Images alone can mislead. In December, as the comet's elongation increases and flagship telescopes regain access, expect a new wave of high-resolution imaging and spectroscopy. And looking ahead to 2026, favorable Jupiter geometry could offer another window for study if 3I/Atlas survives its solar encounter. For now, the best toolkit is a critical eye. Compare images across dates, cross-check photometry, question dramatic reports, and remember that color isn't chemistry without spectra. The global community, from professionals to backyard observers, is watching together. The story isn't over. It's just about to turn another page. Official documents point to technical constraints. Hubble's 50-degree and JWST's 85-degree solar avoidance angles, plus multi-week data pipelines and strict proprietary holds. Despite these explanations, the absence of real-time updates on an interstellar object with a carbon dioxide-dominant coma, sunward plume, and reports of a green tint has left major scientific questions open. No peer-reviewed spectra confirming the coma's chemistry are public, and the full implications of the brightness scatter remain unaddressed. As Mars orbiters prepare for a close pass at 0.19 astronomical units, the next images and spectra, subject to 24 to 48-hour downlinks, could finally break the information bottleneck. Until then, the 3I/Atlas case shows how institutional caution and technical limitations can shape what the world sees and doesn't see about the rarest visitors to our solar system. The waiting finally ended, but not in the way anyone expected. At 14:23 Universal Time Coordinated on October 29th, 3I/Atlas reached perihelion. Its closest approach to the Sun ground-based observatories around the world had their instruments trained on the comet's predicted position. What they captured in those first hours would ignite a firestorm of debate that continues to this day. Dr. Sarah Chun, observing from Cerro Tololo in Chile, was one of the first to notice. The brightness spike was unlike anything I'd seen in 20 years of comet observation, she later wrote in her observation log. Within 6 hours, 3I/Atlas had brightened by nearly 4 magnitudes. But it wasn't a steady increase, it was pulsing. The photometry data told a strange story. Every 4.7 hours, the comet would surge in brightness, then dim again. Not the chaotic flaring of a fragmenting nucleus, but something rhythmic, something almost deliberate. By October 30th, amateur astronomers worldwide had confirmed the pattern. Forums exploded with speculation. Some suggested a rapidly rotating nucleus with asymmetric outgassing. Others pointed to the possibility of a binary system, two objects orbiting each other, taking turns facing the sun. But neither explanation quite fit the precision of the timing. Then came the color data. On October 31st, spectroscopic observations from multiple ground-based facilities revealed something unprecedented. The green emission that amateur astronomers had reported back in August hadn't faded. It had intensified, but the spectral lines didn't match dicarbon or cyanogen. They didn't match any known cometary emission at all. Dr. James Kowalski at the European Southern Observatory was the first to publish preliminary findings in an astronomer's telegram. The emission features centered at 517 nanometers and 519 nanometers show no correspondence with standard cometary chemistry models. The line profile suggests molecular transitions, but from compounds we've never observed in the interstellar medium or in any known comet. Within hours, other observatories confirmed the findings. The green glow was real, it was getting stronger, and nobody could explain it. NASA's statement, released on November 1st, was carefully worded. Observations of 3I/Atlas continue to reveal the unique nature of this interstellar visitor. While some spectral features remain under investigation, all data are consistent with natural cometary processes involving complex organic chemistry. But the statement did little to quiet the growing unease. On social media, the hashtag What is 3I/Atlas began trending worldwide. The conspiracy theories that had simmered during the blackout now boiled over. Some claimed the object wasn't a comet at all. Others suggested it was under intelligent control. A few even called it a warning. On November 4th, the data from a Mars flyby finally arrived, and it changed everything. The ExoMars Trace Gas Orbiter had captured something unexpected during its October 3rd pass. While the resolution was too poor to resolve the nucleus, the photometry data revealed something extraordinary. During the brief 47-minute window when TGO had line of sight to 3I/Atlas, the comet's brightness had pulsed exactly twice, with the same 4.7-hour periodicity that would later be observed at perihelion. But there was more. The multi-gas orbiter, operating in spectrographic mode, had detected something in the comet's extended coma, a faint but unmistakable emission line at 21 centimeters, the neutral hydrogen line. Not unusual by itself, but the signal was modulated. It wasn't random noise. It repeated in a pattern. 3 short pulses, 3 long, 3 short. The international space community went silent for nearly 48 hours. Behind closed doors, emergency meetings were convened at NASA, ESA, and space agencies around the world. The data were reviewed, rear-viewed, and checked for instrument errors. The findings held. On November 6th, a joint statement was released from the International Astronomical Union, endorsed by every major space agency. Recent observations of interstellar object 3I/Atlas have revealed unusual but not unprecedented behavior. The detected hydrogen emissions and periodic brightness variations are being studied intensively. While some characteristics differ from previously observed comets, all available evidence points to natural processes. Scientific analysis is ongoing, and further observations are planned as the object becomes accessible to flagship telescopes in December. The statement raised more questions than it answered. What natural processes could produce a modulated signal? Why the careful emphasis that the behavior was not unprecedented, when clearly no one had seen anything like this before? On December 3rd, as predicted, 3I/Atlas's solar elongation finally exceeded JWST's 85-degree threshold. The telescope immediately pivoted toward the comet for the most anticipated observation in modern astronomy. The NIR spec data came down on December 5th. The full analysis would take weeks, but preliminary findings were rushed through review and released on December 10th in a special session at the American Astronomical Society meeting. Dr. Elena Vasquez, the principal investigator for the JWST observations, stood before a packed auditorium and a global live stream audience. Her hands trembled slightly as she advanced to the key slide. The spectroscopic analysis confirms that 3I/Atlas has a composition unlike any object in our solar system, she began. The coma is dominated not by water ice, but by a complex mixture of carbon dioxide, methane, and organic molecules, including amino acids, nucleobases, and what appear to be complex aromatic hydrocarbons. A murmur ran through the audience. This was extraordinary, but not entirely unexpected for an interstellar object formed in a different stellar system. But there's something else, Dr. Vasquez continued. The high-resolution imaging has resolved the nucleus. It's not a single object. It's a cluster, hundreds of smaller bodies, each between 50 and 300 meters across, held together in a loose gravitational formation. The periodic brightness variations we've observed are caused by the rotation of this cluster, with different facets presenting to the Sun over the 4.7-hour cycle. She paused, her next words carefully chosen. The geometric arrangement of these bodies is unusual. While natural clustering can occur in comet-like objects, the distribution shows a degree of organization that we're still working to understand. Several components appear to be reflective, far more so than typical cometary ice or rock. The spectral signature suggests metallic or silicate surfaces with very high albedo. The implications hung in the air, unspoken but understood by everyone in the room. The final revelation came not from the scientists, but from an unexpected source. On December 18th, a radio astronomer at the Very Large Array in New Mexico, conducting routine observations of interstellar hydrogen clouds, stumbled across something that would make history. Dr. Marcus Webb had pointed his array toward 3I/Atlas almost on a whim, curious about the hydrogen emission detected by the Mars orbiter. What he found sent him racing to his supervisor's office at 3 a.m. The 21-centimeter emission was still there, but now that 3I/Atlas had moved away from the Sun's radio interference, Webb's instruments could resolve it with far greater precision. The signal wasn't random. It contained structure, repeating patterns embedded within the pulses. Over the next 72 hours, as word spread quietly through the astronomical community, teams around the world confirmed the findings. The signal repeated every 4.7 hours, coinciding exactly with the comet's rotation period. The pattern was complex, but not random. It contained what information theorists called structure redundancy, the hallmark of information encoding. On December 21st, after intense debate and consultation at the highest levels, a decision was made. The discovery could not be contained any longer. At 1800 hours Universal Time Coordinated on December 22nd, 2025, the President of the United States, flanked by the NASA Administrator, the Director of the ESA, and representatives from space agencies worldwide, addressed the world. Today, humanity stands at a threshold. After months of observation and rigorous scientific analysis, we can confirm that interstellar object 3I/Atlas exhibits characteristics that suggest it may not be entirely natural in origin. While we stress that our understanding is still evolving, the evidence indicates the presence of structured materials and what may be a form of organized signal transmission. The President paused, the weight of the moment evident. We do not yet know if this represents an artifact from an extraterrestrial civilization, a natural phenomenon we have never encountered, or something between those possibilities. What we do know is that 3I/Atlas is heading out of our solar system. Its trajectory will take it back into interstellar space by mid-2026. We have a brief window, perhaps our only window, to learn what we can. To that end, I am announcing Project Threshold, a rapid development mission to launch an interceptor probe within 6 months, with the goal of conducting a close flyby of 3I/Atlas before it passes beyond Jupiter's orbit. This will be a joint international effort, representing the combined capabilities of humanity's space programs. Whatever 3I/Atlas may be, messenger, remnant, or mystery, it has reminded us that we are not alone in our questions. We look to the stars not with fear, but with wonder, and with the determination to understand our place in a cosmos far stranger and more magnificent than we imagined. In the days following the announcement, the world grappled with the implications. Religious leaders, philosophers, scientists, and citizens from every nation debated what 3I/Atlas meant for humanity's understanding of itself and its place in the universe. The conspiracy theorists who had been dismissed during the blackout found themselves uncomfortably vindicated. Not in their wildest theories, but in their insistence that something had been hidden. Trust in scientific institutions took a hit, even as those same institutions scrambled to be more transparent about Project Threshold's progress. The amateur astronomers who had kept watch during the silent months became celebrities overnight. Their persistence, their refusal to look away, had kept the pressure on until the truth emerged. As for 3I/Atlas itself, it continued its journey, growing dimmer each night as it receded from the sun. The green glow faded. The signal, tracked by radio telescopes worldwide, began to weaken but never quite disappeared. Every 4.7 hours, like clockwork, it pulsed. 3 short, 3 long, 3 short. Was it a beacon? A warning? An invitation? The simple electromagnetic echo of a long-dead civilization's technology tumbling through the void? Project Threshold would launch on June 15, 2026. If all went according to plan, the probe would reach 3I/Atlas in October that year, just as the object crossed Jupiter's orbit. Humanity would get one close look, one chance to solve the mystery. But as Dr. Chen wrote in her journal on December 23rd, watching 3I/Atlas through a telescope for what might be the last time from Earth, perhaps the greatest discovery isn't what 3I/Atlas is, but what it's made us ask. For the first time in history, we're not wondering if we're alone. We're wondering what we'll do when we finally have an answer. The object that had arrived as a ghost generated conspiracy theories during its silence and revealed itself as something beyond our experience, continued its voyage. Behind it, it left a changed world, one that now looked at the stars knowing that something, somewhere, might be looking back. The story of 3I/Atlas wasn't over. In many ways, it had only just begun.